Today we're looking at the drive system for a riding mower. Some parts for this system include internal gear pumps, fans, a fluid control device, and a dead bird. This machine was actually scrapped because it ate a bird. That bird's name was Pete, and he's graciously donated part of his afterlife to help us explain the system. Pete's hoping that studying this lawnmower will help him find peace and move on to the other side. Here's a diagram of our system. The engine powers the pumps, which cycles hydraulic oil through the hydro motors to turn the wheels. There's actually two pumps in each of these diagrams. There's a primary pump that does most of the work, and an internal gear pump which pushes oil into the casing of the primary pump at high pressure. This helps it avoid cavitation and run efficiently, as well as cycle fresh hydraulic fluid into the pump from the tank, which it pulls through a filter. Pete, which of these systems would you like to study in more detail? Alright then, internal gear pump it is. The internal gear pump is connected to a funky fluid control device, illustrated here. The arrows are to show the direction the fluid is moving. What's happening here is that the pump is taking fluid from the tank and pushing it into the casing. The other pump then sends it to and from the hydro motor in a loop. The lawnmower can be reversed and forwarded quickly by changing the direction of this flow, meaning no complicated gear trains. Meanwhile, fluid is slowly exiting the casing through a constriction at the same rate it's shoved in by the gear pump. All the pressure it generates is actually from resistance in the system. The volume of fluid in the casing is constant, so it must reach high pressures to satisfy conservation of mass. Pete, you feeling any better yet? Would seeing the gear pump move help? Alright, on to the math. Let's start with specific speed and diameter. From our pump measurements and some performance specs, our specific speed is 7.51 times 10 to the minus 3, and our specific diameter is 0.276. The main model we utilize here is the continuum model, as it lets us use pressure instead of collisions for every atom. As you can see, the specific diameter is pretty typical for a centrifugal pump, but the specific speed is very low. This indicates that the necessary pump for our intended purpose produces a very high pressure at a very low flow rate. There are no turbo machines that will operate efficiently in these conditions. This means that a positive displacement pump is the better choice and validates the usage of such a pump for this application. There are still a few types of positive displacement pumps that could be used in this situation. So out of all the options, why use a gear pump? Well, piston pumps aren't great because they have lower efficiency, and the flow rate isn't constant. Because of the constant pushing of the piston, the flow through the pump pulsates. Peristaltic pump is higher risk since the friction against the tubing inside makes it prone to leaking and ruptures. They are very unsuitable for higher RPM applications and would likely fail at the around 2400 RPM rotation as expected of the pump in our application. Rotary vane pumps work much better for lower viscosity fluids, and we're using motor oil, so it wouldn't exactly work here. So gear pump is ideal. It works better with high viscosity and high pressure fluids, which is exactly our situation. It provides a relatively steady flow for use in the rest of the system as well. So the next question is internal or external gear pump? Well, internal gear pumps are much less temperature sensitive than external gear pumps because they have larger clearances, so more room for thermal expansion. The higher clearance also makes internal pumps better for high viscosity fluids like motor oil. The oil in our pumps sees a huge fluctuation in temperature, from -23 to 90 degrees Celsius according to the spec sheet. This means that an internal gear pump is a better choice for this application. Our final piece of analysis is the Reynolds number. The Reynolds number is equal to rho UL over mu, and basically is a measure of how turbulent the flow is. We also take advantage of the mean flow approximation to calculate U. Using the area average speed is very helpful since we're dealing with weird areas. Mu is found using kinematic viscosity times density, which are both in the spec sheet. The final number is 108.75 kilograms per meter second. Rho equals 870 kilograms per meters cubed, also from the spec sheet. U and L are a little funky because the gear is moving. For L, we took an average from the minimum to maximum length, which was 5.334 millimeters. For U, we use the equation U equals Q over A, with A being the depth times that area average length we just calculated. Q is specified in the spec sheet. Putting all of this into the equation for the Reynolds number, we get 0.0866. That's pretty low. This means that the Reynolds number approaches 0, so it's reasonable to assume it's laminar flow. This validates our streamlines, which will remain valid up until a Reynolds number of about 500, which is when it exits the laminar regime. This number was found with the highest rated speeds for the system, making the actual working range between 0 and 0.0866, so our laminar assumptions are valid. To analyze this further, we could use the Stokes equations, since we meet the requirements for it. However, we're almost out of time, and Pete is very frustrated by the math, so as any good lecturer will do, we'll leave this as an exercise to the viewer. Pete, has this helped you find closure and move on? Pete, what you got there? Well, I guess that's one way to find inner peace. Anyway, thanks for watching.